A rare sight at Yellowstone National Park today, a hydrothermal explosion in broad daylight. It's not the lava like you typically see from a volcano. Instead, it's rock and mud and steam all blended together to give us that.
This is not the story you think you know. Yes, Yellowstone looms large over any conversation about volcanic threats. A restless giant whose repeated warnings echo beneath the surface of America's most famous national park. The world's largest collection of geysers, pools boiling at 192 degrees Fahrenheit, and a magma chamber that stretches for miles. These are icons of hidden power. But Yellowstone, for all its notoriety, is not alone. In recent years, scientists have found signals, earth rumbling where it used to be quiet, the ground lifting in places where it had slumbered for centuries, and magma shifting beneath the surface in ways even seasoned volcanologists find noteworthy. All across the planet, other supervolcanoes command attention. What will happen when not just one, but several of these geological giants stir at once? When a system with the ability to reshape continents displays signs of renewed life, do we fully grasp what's at stake? Today, we journey into the shadowy depths beneath our feet, exploring new geological discoveries, the science behind supervolcanoes, and earthquakes that ripple far beyond local fault lines. Every chapter begins with a new warning, each tied to scientific findings. Yellowstone isn't the only threat we face, and as you'll see, the ground may not be as stable as it appears. Stay with us as we uncover the hidden story of Earth's most dangerous volcanoes, the evolving science that tracks their every move, and the forces that could, in a single instant, change the world as we know it. Is this simply a coincidence of restless geology, or a pattern that demands our attention? Chapter 1. Yellowstone Supervolcano. New warnings. Could Yellowstone really erupt in our lifetime, or is this just media hype? The question echoes through the halls of science and public forums, sparked anew by rising ground levels, clusters of micro-earthquakes, and consistent geothermal activity. Yellowstone's reputation has a solid basis. It sits atop a vast volcanic system, feeding a network of geysers that boil at temperatures as high as 192 degrees Fahrenheit. Recent observations highlight subtle yet notable swelling in regions of the caldera, a phenomenon closely watched but not unprecedented. Combined with recurring seismic swarms and the natural dynamic movement of magma, these become the focus of ongoing study and monitoring. But what do these signals actually mean? Experts stress that while seismic activity varies and ground movement occurs, these do not point to an immediate threat. Yellowstone last experienced a major eruption more than 70,000 years ago, and most disturbances reflect the complex, ever-changing interactions within its volcanic reservoir. The lava here covers a broad spectrum, from basalt to rhyolite, a chemical diversity that reflects a restless, evolving system beneath. While Yellowstone certainly commands attention, the majority of events here are well within the range of historical variability. To track these cycles, scientists monitor over 1,500 earthquakes in Yellowstone each year, most too subtle to detect without instruments. More than 50 seismometers capture the frequency, location, and depth of seismic events. The US Geological Survey also uses GPS and satellite radar to detect ground movement down to millimeter scale precision. When these measurements show uplift or unusual deformation, research teams investigate further, reviewing patterns against decades of historical data. Meanwhile, the park's hydrothermal features, hot springs, mud pots, fumaroles, are also under constant scrutiny. Scientists track changes in water chemistry, temperature, and gas emissions, mobilizing if anything shifts outside established norms. This immense data set tells us that volcanic systems like Yellowstone's are dynamic by nature. The interconnected changes observed today reflect a living volcano, but so far, not the signs of an impending eruption. Chapter 2. Supervolcanoes beyond Yellowstone. Wake up! Why are volcanoes far beyond Yellowstone stirring now? If Yellowstone is the headliner, other supervolcanoes across the globe are also on the radar of scientists. Recent observations highlight increased activity at supervolcanoes long considered dormant or quiescent. These include broad calderas that haven't erupted in tens of thousands of years, but now show ground deformation, evolving gas emissions, and spikes in deep earthquakes. But is this a new phenomenon? The answer may lie in Earth's ongoing tectonic cycles. Slow-moving plates exert pressure, leading to periodic pulses of volcanic activity worldwide. Seismometers in these regions detect tremors, sometimes reminiscent of patterns seen at Yellowstone. Scientists carefully follow these signals to determine whether they're part of natural, long-term cycles or indicate something more consequential. Notable calderas under observation include Italy's Campi Flegrei, New Zealand's Taupo, and Indonesia's Toba, all supervolcanoes with the potential for globally significant eruptions. Recent years have brought news of ground uplift beneath Campi Flegrei's densely populated surroundings, hydrothermal shifts and deep lake venting at Taupo, and subtle changes in gas emissions at Toba. Each is subject to continuous monitoring by national and international agencies. There is ongoing scientific debate over whether apparent global patterns of supervolcano unrest are linked or simply coincidental. Ideas such as minor changes in the Earth's gravitational field or shifts in the planet's magnetic field influencing volcanism remain hypothetical. For now, researchers collaborate and share data, aiming for a clearer picture of global volcanic threats. Chapter 3. Shishaldin Volcano, Red Warning. What prompts scientists to issue a red warning at Shishaldin? Red warnings are the highest alert level and are issued when an eruption is imminent or ongoing with significant ash emissions. Shishaldin, a highly active stratovolcano in Alaska, is a prime example of prompt detection and warning communication. According to Dr. John Power of the Alaska Volcano Observatory, a red warning means an eruption is either underway or imminent. In recent years, Shishaldin has produced strong ash emissions, ongoing tremors, and visible lava flows. Shishaldin shows that critical volcanic activity is not limited to famed supervolcanoes. The Aleutian Arc, where Shishaldin sits, is an intensely active region where rapid tectonic subduction drives frequent eruptions. The red status is a call for immediate action, air traffic advisories, local preparedness checks, and enhanced monitoring of changes in eruption style or ashfall distribution. During such periods, response systems mobilize. Authorities coordinate with local communities for risk communication, while scientists deploy mobile sensors and fly reconnaissance missions to track ash clouds and lava movement. Shishaldin's ongoing activity provides important insight into volcanic risk management, serving as a model for timely alerts and public safety efforts for other volcano-prone regions. Chapter 4. Ground inflation, a ticking clock. What does it mean when ground levels start to rise near volcanoes? Throughout volcanic history, ground inflation has preceded several eruptions. Gradual lifting of the land, whether fractions of an inch or more, is a classic signal that magma may be accumulating beneath the surface, increasing pressure in underground chambers. At Yellowstone, ground deformation is meticulously tracked using both satellite radar and dense GPS networks. Each episode is analyzed alongside changes in gas emissions and seismicity to separate routine breathing from signs that may precede eruption. Most ground movement recorded at Yellowstone and other supervolcanoes is within typical ranges, but ongoing monitoring is crucial due to the potential consequences of sudden, large-scale inflation. Even subtle ground deformation can have local impacts. Shifts in the earth can alter water tables and the flow of hydrothermal features. Hot springs may change course, geysers can erupt more frequently, and groundwater chemistry can fluctuate, sometimes affecting local water quality. Scientists use aerial surveys and topographical scanning to build detailed models, forecasting which landscapes are most likely to experience changes. These observations help inform contingency planning for communities near volcanic regions. Chapter 5. Earthquake swarms signal deep unrest. Are earthquake swarms the first sign of something bigger? Clusters of small earthquakes, referred to as swarms, often occur where magma is moving or fracturing rock deep below the surface. At Yellowstone and other active volcanoes, scientists track these swarms carefully, since they can be signals of changes within the magmatic system. Individually, these earthquakes are rarely felt, but their timing and location provide valuable hints about subsurface activity. A notable uptick in swarm activity may suggest new intrusions of magma or increased interaction with hydrothermal fluids. Most swarms at Yellowstone are benign. Some reflect routine adjustments or the response to shifting fluids. Scientists rely on changes in patterns, such as increased frequency, higher magnitudes, or a shift in location, to decide when extra attention is warranted. New computational tools, including AI-assisted pattern recognition, are now applied to seismic data, providing deeper insight into whether a swarm suggests a harmless episode or a potential precursor to more notable activity. This integration of technology enhances our ability to foresee and prepare for possible volcanic unrest. Chapter 6. Lava Chemistry, Basalt to Rhyolite. How does the chemistry of volcanic lava impact the eruption's explosiveness? Lava chemistry is crucial in understanding how a volcano will behave. At Yellowstone, eruptions have produced everything from relatively fluid, low silica basalt to thick, viscous, silica-rich rhyolite. Rhyolitic magma tends to trap gases, building up pressure that can be released explosively. Basaltic magma, by contrast, usually produces less violent eruptions as it allows gases to escape more readily. Scientists such as Dr. Catherine Hickson explain, volcanic eruptions are shaped by the chemistry of their magma. The more silica-rich and viscous the melt, the more it traps gas, and the more explosive the eruption. Researchers regularly collect and analyze samples from recent and historical eruptions, using their chemical signatures to reconstruct the volcano's internal history. Changes in sulfur or certain mineral concentrations in magma inclusions can also indicate that new material is rising from deeper in the mantle. By studying the composition of gases, crystals, and lava, geologists are better equipped to forecast how future eruptions might unfold and how much warning the system may provide. Understanding these chemical processes is one of the keys to predicting the potential scale and style of volcanic eruptions. Chapter 7. Supervolcano eruption timelines revealed. When did these supervolcanoes last erupt, and what does it mean? The most recent major volcanic event at Yellowstone occurred about 70,000 years ago, although the system has produced smaller eruptions and hydrothermal explosions since then. Other supervolcanoes show similar histories, long periods of quiescence punctuated by occasional major events. Scientists establish these timelines through dating of volcanic rocks, analysis of ash layers, and mapping of caldera formations. Though the timing of previous eruptions is instructive for gauging recurrence intervals, it is not reliable for precise predictions. Volcanoes do not erupt on set schedules, and the timescales involved span tens of thousands to hundreds of thousands of years. Instead, current changes in seismicity, gas emissions, and ground movement are given priority as warning signs. Some periods of heightened activity lead only to minor eruptions or increased steaming, which can relieve pressure and delay larger events. In other cases, a long period of inactivity can precede a sudden major eruption. Scientists model these behaviors using computer simulations that take into account known histories and physical variables, seeking patterns that may support long-term forecasting. Chapter 8. The threat potential defined. How is the threat potential of a volcano measured? Volcanic threat potential is a multidimensional calculation that considers eruption history, proximity to population centers, monitoring data, and the range of volcanic hazards. Yellowstone rates extremely high, not because of frequent eruptions, but owing to the possible global impacts of its next major event. The USGS periodically publishes updated assessments of volcanic threat in the United States, ranking volcanoes on scales that quantify population exposure, aviation hazards, and eruption potential. Other volcanoes, such as Alaska's Shishaldin, move up risk lists not just because of active eruptions, but also due to their position in busy airspace or close to local communities. The ripple effects of a major eruption, increased ash in the atmosphere, disrupted transportation, and impacts on water and agriculture are all factors that feed into these rankings. A threat assessment's goal is to sharpen both scientific focus and public awareness, not to create panic, but to support readiness planning in areas where volcanic hazards could have the widest or most severe impacts. Chapter 9. Magma Chambers, Science Unveiled. What are magma chambers, and why are they so consequential? Beneath every active volcano is a magma chamber, a subsurface reservoir of partially molten rock feeding eruptions and geothermal features. In Yellowstone, seismic tomography has revealed a complex and sizable magma body, composed of multiple interconnected pockets at varying depths. Dr. Michael Poland of the USGS describes this magma system as vast, layered and dynamic, with shifts that influence ground movement and volcanic activity at the surface. Changes within a magma chamber can indicate new influxes of material, cooling and crystallization, or gas escape. Seismologists map these features by interpreting earthquake waves, while geochemists analyze volcanic gases and heated groundwater for chemical clues. Together, these data streams improve understanding of the pressure and stability within the system. Recent advances, such as muon tomography, now allow for even more detailed imaging, mapping the density and structure of magma reservoirs deep beneath the ground. Ongoing research helps refine models, supporting efforts to predict both routine and potentially hazardous changes in volcanic systems. Chapter 10. The Ring of Fire Connects All. What connects so many volatile volcanoes in a single region? The Pacific Ring of Fire is a zone encircling the Pacific Ocean basin, characterized by high seismic and volcanic activity. This horseshoe-shaped belt marks the boundaries of multiple tectonic plates, including the North American, Eurasian, Pacific, and Indo-Australian plates. Most volcanoes in this region occur where plates are subducting beneath one another, generating the conditions necessary for magma formation. Alaska's Shishaldin, for example, is part of the Aleutian Arc, a direct product of oceanic crust subducting beneath continental plates. Stress and pressure changes in these zones resonate across broad areas, sometimes resulting in clusters of eruptions or earthquake swarms at distant yet tectonically related sites. Connections between eruptions in different sectors of the Ring of Fire remain an area of active research. Significant seismic or volcanic events can redistribute stress along fault lines, and circulating mantle heat can influence volcanic arcs across great distances. Monitoring these interactions is crucial for hazard assessment, particularly given the population density and infrastructure across much of the Pacific Rim. Chapter 11. Tectonic Plates and Supervolcano Triggers. Can earthquakes trigger eruptions, or are the two phenomena independent? Traditionally, earthquakes and volcanic eruptions are seen as related but distinct. Earthquakes primarily result from tectonic plate movements, while eruptions are driven by magmatic and volatile processes. In reality, large earthquakes can sometimes trigger or accelerate volcanic activity, particularly if the system is already under stress. For example, strong nearby tremors can fracture and rupture rock near a magma chamber, allowing for gas escape or magma migration. This phenomenon has been observed in several volcanic regions where major earthquakes preceded or coincided with subsequent eruptions or increased geothermal activity. However, most earthquakes in volcanic areas do not trigger eruptions. The relationship depends on multiple factors, including the state of the magmatic system at the time. Researchers use high-resolution seismic arrays and geophysical surveys to monitor both types of activity, studying their interactions and potential implications for forecasting. Chapter 12. Gas emissions and volcanic breath. Do changing gas emissions serve as reliable warnings? Volcanic gases, especially carbon dioxide and sulfur dioxide, offer important early clues to changes in a volcano's subsurface system. As magma rises or shifts, These gases are often released in measurable quantities through surface vents, fumaroles, or diffuse soil emissions. Monitoring equipment, ranging from ground-based sensors to satellites, tracks changes in gas composition and concentration. Scientists like Dr. Emily Johnson have emphasized that rising gas emissions, particularly of sulfur dioxide, can indicate new magma rising and increased potential for eruptions. At Yellowstone, the rates and chemistry of gas emissions are continuously analyzed, and any substantial, unexplained deviation triggers further investigation. Significant volcanic eruptions, especially from large calderas, can inject vast quantities of sulfur and ash into the atmosphere. These emissions can cool global temperatures and disrupt weather, as seen after the 1815 eruption of Indonesia's Tambora. Ongoing monitoring of volcanic breath is critical, not just for detecting unrest, but for understanding global climate impacts. Chapter 13: Antipodal Effects – Global Repercussions. Can an eruption here affect the other side of the planet? The most powerful eruptions and earthquakes can have global atmospheric and occasionally seismic effects, while antipodal triggering, where an event on one side of the planet causes another on the opposite side, is extremely rare and not established as a routine mechanism. Large eruptions can affect the entire globe by dispersing ash and gases into the stratosphere, impacting climate patterns and circulation. More broadly, intense eruptions or earthquakes can send seismic waves around the planet, and in some cases, alter stress regimes in distant tectonic regions. This interconnectedness is a subject of research, as supercomputer simulations seek to map out potential domino effects from massive earthquakes or blasts. As global datasets improve, researchers are becoming better able to track the wide-ranging consequences of rare but extreme geological events. These explorations inform disaster preparedness and scientific understanding of Earth's complex, interconnected systems. Chapter 14: The True Cost of Complacency. What happens if we ignore supervolcano warnings? Can science afford to be wrong? History shows that unpreparedness in the face of volcanic disaster carries immense costs. Explosive eruptions have caused regional devastation, climate anomalies, agricultural collapse, and societal disruption. Modern technology, satellites, seismic arrays, gas sensors, have revolutionized monitoring and forecasting abilities. Scientists emphasize that ongoing investment in monitoring and communication is essential. Every false alarm has its risks, including public fatigue and complacency. But the dangers of missed warnings are far more dire. Recent signs of ongoing activity at Yellowstone and elsewhere highlight the importance of vigilance, preparedness drills, infrastructure investment, and science-literate leadership. The communities most exposed must balance the costs of readiness with the need to accurately assess genuine risk. It falls to scientists to communicate findings in understandable ways for policymakers and the public, ensuring that signals, however faint, are recognized and acted on in time. Chapter 15: Restless Earth – Unfinished Story. Is there ever truly such a thing as geological peace, or only quiet between storms? The planet's surface is always dynamic, shaped by cycles and forces far greater than human timescales. From Yellowstone's geysers to active volcanoes worldwide, the Earth is continuously changing. Every GPS measurement, every subtle quake, every change in water chemistry is part of an ongoing commentary from our planet's interior. Despite enormous scientific advances, the challenge of prediction remains. Uncertainties will always exist in geology. Nature's clock follows cycles far beyond any human calendar. The best approach is to remain alert, committed to monitoring, and responsive to new discoveries. Yellowstone is not alone. Around the globe, volcanoes continue to stir, their activity reflecting both ancient cycles and new changes within our planet. Preparedness and scientific vigilance form our best defense. Each new signal, Every minor quake, each unusual measurement, reminds us that our story with supervolcanoes is one chapter in the planet's restless, ongoing narrative. Stay informed, stay vigilant. The ground below may hold more secrets than any of us have dared imagine.